What you may have noticed in the previous examples is that there's very specific functions, especially when it involves division, that when you integrate to infinity converge, and others that don't. And another thing you might notice about a lot of the examples we look at is typically we're only going to integrate to infinity if the function has a horizontal asymptote at 0. Because, a simple graph can illustrate the point I'm trying to make. Say, for example, a function does not have a horizontal asymptote, or it has a horizontal asymptote, say, at 2 or something else. If you're going to integrate this to infinity, if it doesn't head to 0 and you're like if you have literally an infinite width of on your x-axis and the height does not trend to 0, essentially what we're going to have is infinity times some height, and of course infinity times, it will definitely be an infinite amount of area. But it's only specifically when the function heads to 0. And only, how I like to phrase it is it's only going to converge if it heads fast enough. Because this function heads to 0 pretty rapidly, and it converges the area under that curve. Whereas other functions can still even head to 0 and still not converge. So that's kind of a thing to pay attention to. And it turns out there's a simple generalization that you can make based on the general structure of the antiderivative of 1 over x to the p. And, looking at the two cases we've looked at, 1 over x from 1 to infinity diverges, whereas 1 over x squared integrated from 1 to infinity converges. So there's a very distinct answer. And what it turns out, from theorem number 2 from our textbook is that whatever the power is on 1 divided by x, it always converges if p is greater than 1, and it will always diverge if p is less than 1 or equal to 1, as it is with the reciprocal function. So the reciprocal function diverges, and any smaller power, so let's say we had p to the 1/2 or p to the 1/3, or even if p was negative, then it would just be a power function, a proper polynomial, assuming it's whole. But basically, assuming p is greater than 1, even say 1.1, it will converge. And you can see easily why this is true by just integrating 1 over x to the p in each case. And also, all this being said, since these are involving limits, sometimes we may need tactics for solving limits, such as algebraic skill, L'Hopital's rule, graphical numerical approximation. There's all sorts of ways that we can solve limits. And so let's just look at another example. Additionally, say we were integrating to minus infinity. Similarly, we would need to extract that in the form of a limit. And you can always create a graph of the function to try to visualize, okay, what is it that I'm doing? So say I don't have any idea what this function looks like. I could always type x e to the x in a calculator to sort of see what's going on. And if we look at this function, it appears to be going down under the curve and flattening out greatly because, well, an exponential function has this sort of shape to it where on the left-hand side it trends to 0. And since we're on the negative side and multiplying by x, it's going to be negative instead. And maybe if we made our y-axis a little bit tighter, we could see this a little bit better. But notice it has this sort of shape to it. And essentially, what we can tell is it appears as though it's heading towards 0 very rapidly. So I'll go ahead and create a little sketch. Because again, it is a definite integral. It does correspond to area, and we can use our visualization of the curve as a way of helping think about the answer. So that's a little bit off. Let me try to draw that just a hair better. But it's going to look something like this. And it appears to have a horizontal asymptote towards 0. And essentially what we're looking at is what is the area underneath the curve. I'm expecting us to get a negative answer since it's beneath the curve on that interval. And again, it does not ever actually go to 0 because technically there's an infinite amount of area. We're going to integrate all the way to minus infinity. But again, we need to extract the infinity as a limit in order to proceed. So we would write the limit as t approaches minus infinity of t to 0 of x e to the x dx. And here, as we know, since it's a product of two functions, we probably are going to need integration by parts. And every other tactic of integration we've been learning in chapter 7, you might need depending on solving the integral, right? Because to progress, we need to figure out what's the antiderivative of x e to the x. So by integration by parts and LIATE, we should probably set u to be x, which would mean du is dx. Very simple there. And if once we pick u, dv is everything else. So dv would be e to the x dx. And the antiderivative of that would just be e to the x. And now we could apply integration by parts formula to continue in thinking about our limit. So this must be equal to the limit as t approaches negative infinity. And now this will split into to two terms, uv minus integral v du. So I'd have x e to the x minus integral e to the x dx. And again, these would be integrated from t to 0. And this part of it will be evaluated from t to 0. And as I said in class, usually, let me make this a little larger, I prefer to wait to finish the whole thing to plug in the boundaries of integration as a personal preference. But that would leave me with the limit as t approaches infinity of x e to the x. And of course, the antiderivative of just e to the x is just e to the x. Or again, this is one we might have memorized since it is an example we've seen in class. But anyways, first step, of course, extract the limit. Second step, solve the antiderivative. Third step, plug in the boundaries of integration. Again, 0 is going to go in first here. Careful with 0 because 0 times anything is 0, but e to the 0 is actually going to give us -1. And then that's all going to be minus plugging in t. So it will be minus t e to the t minus e to the t. And all of this will, we would need to know the limit as t approached negative infinity. Sorry, my negative has disappeared because my pen is a little bit too thick. But there should be a negative on there. And now what we need to do is figure out our limits. So from here, the limit of a constant is always a constant. So we know that is just the first part is going to be -1. But then we want to consider, what about the remaining components? So the limit of e to the t as t approaches minus infinity, well, an exponential all by itself will trend to 0 as you go to minus infinity, because essentially it's like e. So again, we're not allowed to do this math, as I've emphasized with limits, but if we kind of pretend as though we could plug in infinity using our imagination, which again, this is mathematical garbage, we can't do this. But essentially, it would look like 1 divided by e to the infinity, or 1 divided by a grossly large number, an infinitely large number. And again, if we divide by infinity, that is essentially going to give us 0. So my point on this one is that this would trend to 0 because it has a horizontal asymptote at 0 on the left side. And additionally, t e to the t, well, that actually matches our original function exactly, which looks like this. So another way I could figure this out is, well, if I'm looking at it towards minus infinity, that would also have a limit of 0. But we could always use other tactics, like, for example, L'Hopital's rule. So let's just go ahead and just review how to do that in this case, because, again, sometimes we might get stuck on a limit if we don't want to rely on a graphical or numerical method. We might want to do it algebraically. But, the limit of -1 is -1, and then we would have minus the limit as t approaches minus infinity of t to the t. And actually, one of the tricks for approaching this, if we wanted to do L'Hopital's rule, would be to actually write it like this: t divided by e to the minus t. Because, I could always take an exponential and write it as a reciprocal by changing the sign on the exponent. And now I could use L'Hopital's rule to solve this, because now if we're looking at this, what we have is something that is of the form minus infinity over infinity, because if we were to plug in infinity here, we'd have infinity. But again, don't want to overly review L'Hopital's rule. But again, just for the sake of review, L'Hopital's rule states that if an integral is a indeterminate form of either infinity over infinity or 0 over 0, remember it has to be specifically one or the other, then its limit will be equal to the limit of the ratio of the derivatives of the original two. So if I just take the derivative of the top, with respect to t, I would have 1. And the derivative of e to the minus t would be negative e to the minus t. And notice what I end up with is, well, this is just negative e to the t, positive t, because it would flip back over. But what I end up with is, again, another limit that's going to head to 0. Because, again, if we were imagining plugging this in, I essentially have 1 over e to the positive infinity. That's going to for sure head to 0. And what I end up with is 1, another, similar, quite simple answer. -1, sorry, as the area under the curve. Or technically it's not under the curve because it's bounded by the x-axis is probably a better way to say what it, how much area an integral calculates, geometrically speaking. Now, another thing that you may be wondering is, can I check improper integrals in my calculator? Because I've shown you guys how to do it before. So obviously, there is no infinity key on a calculator. It's not a number that you can calculate with. But what you could do is say integrate to -1,000 or -1,000,000 or some arbitrarily small number to, get a sense for how big or small this may be. So let's just check it out. Let's see what happens. So we could do, let's just say the integral from -1,000,000. I don't know. I'm just going to pick a really stupidly small number and see what the calculator comes up with as the integral of x e to the x with respect to x. And what it says is 0. That is interesting because that's definitely not right. So I should have tried this ahead of time to see if it did work. Let's try instead using 1,000 and see what it says. Or even 100. If we do 100, it comes up with -1. Kind of interesting that it just gave 0. I actually have no idea why that came up with a 0. But it's obviously not a perfect system for calculating the area to infinity for some reason. Because how well, I don't want to get into how a graphing calculator calculates such an integral. We can even try going to 1,000. But of course, you don't want to be overly reliant on technology. I'll pretend that I did this as an example of, being careful with calculators. But notice they will generally work up until a certain point. Perhaps the integrating to -1,000,000 didn't work simply because it overflowed or something. Who knows why it gave an answer of 0. Very strange and unexpected. But regardless, we can see why it heads towards -1 by simply looking at our answer here. And of course, this is never going to go over the x-axis. How could this possibly be 0 if the area is purely underneath the x-axis? Makes no sense. Anyways, in the next video, we will look at another type about what happens if a vertical asymptote or if we have a double infinity, and we will get into type 2 integrals very shortly.